Okay, we'll now consider continue the discussion of convex sets. So now give a new definition for absorbing set. So suppose we have a linear space. And the C is a convex subset of this X. And it contains 0. Okay, then we call X absorbing if for any lambda. All right, for any X in the set, there exists a lambda such that X over lambda is in C. Okay, so continuing the discussion for the Minkowski's is functional, we know that for every X, we want to find the infimum of this lambda such that X over lambda is in C. And now this, if the set C is absorbing, then we know that this infimum must be finite because we know that there exists at least one of such lambda that makes this in C. Right? So absorbing guarantees that we're going to have a finite Minkowski's functional for any X. Okay, so that's called the absorbing set. Typically, you can think in this way. If we have this whole space, so this is our C, and this is our whole space. Or maybe you can treat it as a linear space, so it could be infinite dimensional. Let me just remove that. Okay, and it contains 0. So it's absorbing means that it doesn't matter where this X is. So if X here or X here or anywhere, you can always shrink it down into this set C. Okay, so just make this lambda large enough, they will be in the C. Okay, this is called absorbing. What is not a absorbing set? You can think in this way. Suppose we have the C like that. So our C is like this. And then in this case, it's in R2. And this is our C. Now in this case, if we have points like here, say, then you know that no matter how, there's no such a lambda that makes X over lambda in C. Okay, although that C contains 0, but you cannot really shrink every X down to C. Okay, so you can interpret this as that if it's absorbing, that means X, the 0 should be an interior point of the C. Okay, like in this case, you can find, you can see that the 0 is interior point, then you can shrink everything back into the C. But it's not the case in here. Okay, so that's the idea. Okay, and also we can define symmetric set. It's not used much in this course, but just since we're already being here, let's just give the definition here. So we say, again, we say that X is linear space. C is a convex subset of X. And again, 0 is in C. And then we call X, sorry, I should say C here. Call the C symmetric. If for any X in C, the negative of X is also in C. Okay, so this is pretty easy to understand, but we're not going to use the symmetric, we're rather just use the consider more or explore more about the absorbing sets in following. Okay, but anyway, since So I give the definition here. Let me also give several properties of them. Give a proposition. Again, the setting is the same as before. We have X as a linear space. We have C is convex in X. We know that 0 is included in C. Now let P be the Minkowski's functional. Of C. Then we show that the following two statements hold. One is about absorbing set. One is about the case where C is absorbing, and the other one is about the case where C is symmetric. Okay, so C is absorbing. If and only if the Minkowski's functional takes a finite value. Second, and C is symmetric. If and only if P is homogeneous. Okay, these two are really easy to verify, so I can just take a few minutes to show it by yourself. I'm not going to give the proof here. Rather than that, I'm going to provide some more or stronger results about the Minkowski's functional as in the following proposition. So what we're going to do here is that, again, setting as above, it's a linear space. C is a closed convex set. Okay, and C contains 0. So again, P is the Minkowski's functional. And then we're going to show the following statements. The first one is the C is always X such that the Minkowski's functional is less than or equal to 1. So these two sets are the same. Second one, the C is bound. If C is bounded, then the Px equals to 0 if and only if x is 0. The third one is that if 0 is the interior point of the set C, then C is absorbing as I draw earlier. And not only that, the Minkowski's functional P is actually Lipschitz continuous. Okay, so this is the very important property, several properties about the Minkowski's functional on a closed convex set in a general linear space. Okay, let's show this. The first one is, let's say I denote S to be the set on the right hand side. Let me just define S to be okay. And on the one hand, I know that if the point X is in S, then since P of X is less than or equal to 1, I know that for any K, the X plus, let's say px is less than or equal to 1, so it is definitely less than or equal to, even less than 1 plus 1 over k, right? So that also means the 1 this is going to be less than 1, the less than or equal to 1 over px. Let's assume that px is non-zero at this moment. So I could add a small number to px so that the px plus epsilon, such that this is in the C, right? So that's why I can choose this epsilon extremely small so that this is still true. Right. This is still true, and this is chosen. This number is chosen such that this x over this is in C. So what I'm trying to say here is that if this is 0, this is the x over px plus epsilon. You think there's a linear space. This is a linear space, so this is like the ray passing through 0 and this x. So then the x will be somewhere here. X over 1 plus 1 over k is somewhere here in between. Right? So now I know this point is in C, and the 0 is in C. So the whole line should be in C. That means this one is also in C. Okay, so now I'm going to define this xk to be the x over 1 plus 1 over x, and I know that this is in C for any k, as I showed earlier, for any integer k, right? And then let k go to infinity. Then I'll see that since C is closed, and this xk goes to x, we know that x must be in C. Okay, so now for any x in S, we show that it's also in C. So that means S is included in C. Okay, so S is included in C. The other direction is easy. If I have x in C, then apparently I know x over 1 will be in C, right? And the p of x must be less than or equal to 1 because p of x is infimum of the lambda. When we divide x by lambda, you get it in C. So that's the infimum lambda. So this means that px is in less than or equal to 1, and that just means that x is also in S. And this concludes the other direction. And since we have both, we know that these two sets are equal. Okay, that's the first one. Second one, if C is bounded, I want to show that P of x is equal to 0 and only if x is equal to 0. Well, if x is already equal to 0, then it's pretty easy to show, okay? So we'll just, if x is equal to 0, it doesn't matter which number you divide, you will just be 0, and that just means you can take the infimum of arbitrary non-negative number, and arbitrary positive number, then you will just get the px. Okay, then obviously px is equal to 0. So we're interested in the other direction. If px equals to 0, can we claim that the x must be equal to 0? Okay, so to show this direction, let's say that if C is bounded, so let's say I have convex set which is bounded and it contains 0, and this means that this C right here can be included in a large ball. Okay, let's say this ball has the radius, so the radius is r. Okay, so that means Since C is bounded, we know there exists R such that the C is included in B0 R. Okay, and what this means is you look at any point in C, you see that along this direction, for example, this is the X in C. Then along this direction, when you scale this X to be large enough, then you will be outside of this ball. Okay, now how large it needs to be? So we know at least when I take the direction of X, but I multiply by R. Say for example, not R, I multiply by, let's say I multiply by R. Then they will be on the boundary. But let's say I chose this R to be so large that, there's no intersection. It doesn't overlap with the boundary of C. Okay, so it's just large enough. If it's not large enough, just double it, double the radius. Okay, and we know that this will not be in C. Okay, and so let's say simply I can do this. Okay, so the point right now is that when I divide X by this value, I know that it will not be in C. Okay, and if you put R larger and larger, it would not be in C at all. So that means your P of X must be bigger than or equal to this number, because Px is infimum of those values that divided by which that this is in C. So that means the Px must be greater than or equal to that. So okay, and from here you can see if X is non-zero, then the P of X cannot be 0. Okay, and the only case possibility is that when X is 0, then Px is 0. Okay, so this will prove the second item. It can only be 0 if X itself is 0. Okay, the third one. Let's say that C is absorbing. So we know that in this case, 0 interior point, and then we want to show that C is absorbing and also the P is Lipschitz continuous. Absorbing is something we have illustrated before. If it's interior point, then the C looks like this. This is 0. This interior point means that I can draw a ball that is completely in C, right? The interior point of C means that there exists epsilon such that the Bx or B0 epsilon is completely in C. Okay, so in this case, let's look at any X in the space. We can always shrink it down back into this ball, right? Like I said, if X is here or here, it doesn't matter how far it is, I can always shrink it down. So how much I should shrink it? I should keep my direction, but make my radius to be make the length to be smaller than epsilon. Say let's say put it as half epsilon. Then I know that I will be inside this ball, this small ball right here. Okay, so I know that it's in the ball, and it is also in C. Right, so I can find a number which is this for the X, so that this is in C. So I can choose my lambda to be X or 2x over epsilon. Okay, then for any X, it is this such that X over lambda is in C. This is what we define for absorbing set. So C is absorbing. And how to show that the Minkowski's functional is Lipschitz continuous? So it's actually by a similar idea here. I know that for any X, because this is true. This is true, so that means my P of X must be less than or equal to this lambda, which is, according to my definition for lambda, is this. So now let's look at the px minus py. I know that the p is subadditive, so I know this is less than or equal to p of x minus y. Right? I just move the p of y to the right hand side. You can see that it's actually from the subadditivity of p. So I know this. On the other hand, I also know that p of y minus p of x is less than or equal to p of y minus x. Same idea. Okay, but these two together tells me that if I take the absolute value of px minus py, it should be less than or equal to the larger one of these two. Okay, I take the maximum of these two. So it will be less than or equal to maximum of p of x minus y and the p of y minus x. Okay, but for either one of them, I know that according to the one here, I know that p of x minus y should be less than or equal to 2 times x minus y over epsilon. And similarly, if I switch x and y, and I will get the same bound on the right hand side because the norm doesn't change, right? So that means this is less than or equal to 2 over epsilon times x minus y. So now what we showed is this p of x minus p of y is bounded by that. So that means the p is Lipschitz continuous with this as the Lipschitz constant. Okay, so that is the that proves the last claim we made. Okay, so now let's consider a corollary of this result. Suppose I have, let's see, we're working on Euclidean space now. I'll explain why. Let's say C is a compact convex set. Compact convex. Convex. Of Rn. Okay, then there exists okay, so we kind of digress from our topic slightly, but we're going to use this fact soon later. So we said that if C is a compact convex set of Rn, now we're restricting ourselves to Rn now, and there exists a m less than or equal to n, which is actual dimension of this C, and C, we show that C is just homeomorphic to this unit ball in the Rm. Okay, so what this means, you can imagine that, say I'll just have a compact convex set in the plane, then I know that I can, this one is actually homeomorphic to the unit ball. Okay, so this is my x in R2, and I know that it's homeomorphic to the unit ball in R2. Just in case that I have this like a two-dimensional convex set in the three-dimensional space, then I'm going to show that this is just again, it's homeomorphic to the ball in the two-dimensional case, right? Imagine that you have three-dimensional space, but my convex set is like just it's living on the plane, like that. Then it's still homeomorphic to the ball. Okay, so this is a pretty. You can actually see that or imagine that, and also it doesn't have to be convex even. You can find a non-convex set like this. It's still homeomorphic to the ball. But the point right here is that I'm going to actually construct the mapping. How do I get the mapping or the homomorphism from this convex set to the ball? And also, I'm going to use this result, following fixed point theorem. And that's why we're interested in this special case right here. Okay, so the proof is a little bit long, but let me first explain the idea. The idea is that if C is compact convex set, then I know that, let's take the example earlier. Let's say that the C is a convex set in R2, and then I know there will be, so that's living in the plane. The C is living on the plane. Now I know there will be 3 points, so that I call them E1, E2, E3. Then I know that E1 minus E3, E2 minus E3, they will span this whole plane. Right? I'll be able to find these 3 points in C such that the E1 minus E3 and the E2 minus E3, these 2 vectors can span the whole R2. Okay, if we're living in the 3-dimensional space, then we can still do this, and they will just span this we call the linear manifold of which contains this C. Okay, so now what I'm going to do is I'm going to take the average of these 3 points. I'm going to get a middle point. So I'm going to take the average of these 2 and I got the middle point, which is E naught. And I'm going to take it as the 1 over 3 of E I is from 1 to 3. And then I can show that this E naught is going to be an interior point of my C. It's the interior point of my C. That means I can draw a ball or draw a disk small enough so that it's in C. Now I can treat this. Say that this E0 is just the shifting from the 0, from the origin. Okay, we shift everything to E. So whenever I consider the point in C, I can shift it back to the origin, which is the same shape. Suppose this is the world we're living in, this is the universe we're living in. So we can always shift it back to the origin. Okay, and then we can, since I have the C like this, and I have this origin as my interior point because it's corresponding to the E naught. So the E naught is the interior point of the C, then the origin is the E naught is the interior point of the shifted C. And then we can define the Minkowski's functional as we did earlier, and this Minkowski's functional will be Lipschitz continuous. Okay, will be Lipschitz, and using this Minkowski's functional, we're going to construct the mapping from this convex set or this convex set to the ball. Okay, so the function we're going to construct completely relies on what the Minkowski's functional is. Okay, and because of the existence of this Minkowski's functional, we can construct that easily. Okay, so that's the general idea. Now let me show that the proof itself is a little bit tedious because we need to take all the situations into consideration. The main idea is like what I plot. Okay, so let's do this. First step, as we said, since this this C is in Rm, so let's say that let E be the smallest linear manifold containing C. So it's like our C is living on this plane in a 3-dimensional space, or C is living on this plane. Then this E, say I have this C, which is living on the plane, and this E is just this plane itself, which is sublinear, which is submanifold, as we explained before. Okay, and then there exists, let's say that the E is m-dimensional. then we know that there exists E1, E2, all the way to En plus 1 in C, such that the E is nothing but the span of E1 minus En plus 1 all the way to En minus En plus 1. This is like what I drew earlier. In this case, M is just equal to 2. So it's like E1 minus E3 and E2 minus E3, which will span the plane. Okay, and then because of this, I will, by the way, the E1 minus En plus 1, they are going to be linear independent. Linear independent. This is how I span them. Okay, and now let E naught to be the average of them, as I showed there. I'm going to find the middle point of the triangle I showed earlier. Okay, and now I want to claim that this E naught, first of all, this E naught is in C. Since all these points are in C, and C is convex, so I'm making an average of them. These weights add to 1, right? So that's why this E naught must be in C. It's in the middle of this, polyhedral or whatever thing formed by this EI. So it's in C. And then I'm going to claim that for any y in the set E, y can be uniquely written or represented y equals to E naught plus the sum of AI EI minus E naught. I is from 1 to M. So what I'm doing here is I'm going to change my remember the picture I showed earlier. If this is the C, this is the E1, E2, this is the E3. Then I found this middle point, which is E naught. And we're going to use E1 minus E naught and E2 minus E naught, these two as the basis of this linear manifold. Okay, so this E naught, again, as I said, is corresponding to the origin. We can shift the whole thing back to such that E naught is equal to the origin. So this will span the whole space. E1 minus E naught, E2 minus E naught will span the whole space. And then I will show that this AI will be unique because this will be a basis. Okay, to see this, so this is what I'm going to prove here. So how do we prove this line? It's just, as you can see, it's necessary, or it's just sufficient to show that this is the basis. EI minus E naught form a basis. So we just need to show that the E1 minus E naught way to EM minus E naught is linearly independent. And they will definitely form a basis because we have M of them. So there must be a basis for Rm or for the set E. Okay. So how do we show this is the linearly independent? Well, let's say by definition, if it's linearly independent, means that if I find a linear combination of them, I get 0. Then what happens is that all the coefficients must be equal to 0. Okay, let's see if this is true for this case. I have a linear combination of them, and I I let them be 0, and let's see what happens. So I know that this, I pull out the EIs, and then I know that I have the sum of I from 1 to m E naught. Sorry, AI E naught. Okay, but E naught is this. E naught is this thing. So I just plug this back in here. I'm going to replace the E naught by 1 over m plus 1 of, remember that this is the E naught multiplied to that. So this E naught is written as this, which is independent of m. Okay, now you can see there's some, let's call this one holds in S as the sum of these coefficients. And then I know I have, if I write it out, then it will be A1E1 all the way to AMEM minus, here I'm going to have S times S over M plus 1 times E1, and S over M plus 1 E2 all the way to S over M plus 1 EM plus 1. Okay, so I'm going to combine the coefficients for E1. I'll have the A1 minus S over M plus 1 E1 plus all the way to AM minus S over M plus 1 EM. And then finally I also have S over M plus 1 EM plus 1. Okay, so still I need to actually put the EM plus 1 into each of these EIs. Okay, and to see this, you can actually see, I can say the sum of AI minus S over M plus 1. Let's see what this one is. This is just equal to the sum of AI. And then for I have m terms of this, and each term has this minus S over M plus 1. So it's MS over M plus 1. But this one is S. So I have S minus MS over M plus 1, and that gives me S over M plus 1. Okay, so this is equal to that. And that means I can replace this by that. And this is actually the same. These coefficients are actually the same sum of these coefficients. Right here, sorry. This should be that. Okay, so what I'm trying to say here is this is essentially just that, and that is the sum of these coefficients. So that's why, once I know this, I can just rewrite the thing above as a, or I can distribute the E m plus 1 into each one of them. So it's A1 minus S over M plus 1, E1 minus E m plus 1, all the way to AM minus S over M plus 1, EM minus EM plus 1. Okay, now we're getting something, because we said that these are linear independent. So we say here, they are linear independent. So that's why this equals to 0. Means that all the coefficients are equal to 0. The coefficients are just like A1 minus S over M plus 1 equals to, everyone has the same value, which is 0. Okay? And it just means that A1 equals to A2 all the way to S over M plus 1. Because the difference of each one of this is equal to 0. Okay, so they all have the same value. Okay, let's call this value C. call this value C. Well, remember that S is the sum of them. S is the sum of them. Sorry, it's M. Right? And each one has the same value C. That means S is just equal to M times C. So this is M times C. So what I have now is M over MC over M plus 1 is equal to C. Then we can claim that C is equal to 0. That means every one of them is 0. And that shows that these coefficients are just 0. And that finishes the claim. They have to be linearly independent. Okay? And they're linearly independent, so they form a basis. And that's why for every y, I can uniquely rewrite it as in this way. Okay? And not only that, since I can actually use this as a basis, I can just define my norm of a y to be the the length or the norm of A. This is just A1 to AN squared, like this. Okay, so if my y is written as E naught plus the sum of AI, EI minus E naught, as from 1 to M, I'm just I'm here. I'm just going to define my norm of y in this way. Okay, now we basically established a relation between the linear manifold and the plane. Okay, so that's our first step. Second step, I'm going to show that the E naught is the interior point for the C. Okay, let's go back to the picture here. So the E naught will be somewhere here, or the picture show this in the middle with triangle. I'm going to show that this is the interior point of this C. Okay, to show this, let's consider the y. We already showed that the y. Here we want to show that E naught is an interior point of C. So to this end, let's look at the y. It's E naught plus, so know that this is how we write the E naught in a unique way. This is AI minus E naught. Okay, and I'm going to use what I just got. I know that I can rewrite this whole thing in this way. So I'm just going to copy it here. This should be copied. Okay, so let me see this. Okay. So what I'm going to do with this one is that, remember again, S is the sum of those AIs. I want to show that the coefficients of this are actually can be small enough, and I also know that the sum of them. Sorry, it's just yeah. So I should have. Sorry, I should have another E naught. So let me see. This part is that. I'm going to show the E naught is the additional one. So let me put it here. Okay. And the E naught is just we know that it's just the average of this EI. So I can put them back into each one of them. Okay. So this means that it's equal to A1 minus plus 1 minus S and plus 1 E1. Right. I'm not doing anything, just rewrite this, decompose this E naught, which is just the average of the EIs from 1 to M plus 1. So that's why I have 1 over M plus 1 for EI, to added to 1 over m plus 1 added to each of these coefficients. That's why I have that. M minus plus 1 minus s, m plus 1 em. And then finally here I have 1 minus s, m plus 1 e, m plus 1. Okay, so first of all, we know that the sum is equal to 1. The reason is the originally, remember that originally the sum of these coefficients is equal to 0. And then here the sum of these coefficients is equal to 1. So that's why the sum of these coefficients should be equal to 1. Or you can easily verify them. So it's already written them here. So it's easy to verify the sum of them equal to 1. And I'm going to show that every one of them will be non-negative when the a is small enough. So we choose, let's say we choose epsilon to be small enough. Such that the 1 minus m epsilon over m plus 1 is greater than epsilon. Okay, so I choose my epsilon so small such that this holds. So this, you can just solve for this. Let's say 1 minus m epsilon greater than m epsilon plus epsilon. Okay, and then in this case, we'll just have 1 greater than 2m plus 1 epsilon. So you can just make your epsilon less than 1 over 2m plus 1. As long as your epsilon is that small, then this will hold. This will hold. Okay, so this is true. Well, if this is true, then if all the AI has the absolute value less than epsilon, we will be able to show that on the one hand, it is less than epsilon. Okay, and this is less than 1 minus m epsilon over m plus 1, as we said that epsilon needs to satisfy this. Well, now let's compare this one with 1 minus, let's say, 1 minus s over m plus 1. I know that according to the definition for s, this should be the ai is from 1 to m plus 1. Well, the AIs all have absolute value less than or equal to epsilon. So that means the numerator right here is bigger than or equal to 1 minus m epsilon. Right? And I know that this will be less than equal to 1 minus s over m plus 1. Okay, so on the one hand, I can see that since this is greater than or equal to 0, I know that this is positive because this is always greater than or equal to 0. So that means this is greater than or equal to 0. Okay, and because the absolute value of this is less than that. Okay, the absolute value of it is less than that, and this is greater than 0. So that means if I take the AI out, if I take this out, it will be still greater than or equal to 0. Actually greater than 0. So definitely it will be less than that. Sorry, this. Right? This will be greater than 0. And that means every one of this is also non-negative. And now I have non-negative values. And I showed that, I said that this, when you add them, all these things up, you get a 1. So that means this is the convex combination of E1 through En plus 1. And that is what Y is. Okay, and that means the Y is actually So y is actually in the convex hull of E1 through En. Okay, so what we have proved so far is that as long as all your coefficients in the representation of y, so as long as the AI is less than or equal to epsilon, then you have y equals in this convex hull. By the way, the convex hull must be in C because the EI through EM plus 1, E1 through EM plus 1 are all in C, and this convex hull must be in C as well because C is convex, right? That's like this is the E1, this E2, E3. So the convex hull is like this triangle, and since they are all in C, and C is convex, so that means this one is the convex hull is in C. So as long as the y or the AIs are less than or equal to epsilon, the corresponding y will be in C. So you can see this is how we represent the y. As long as this one is less than, the absolute value of this one is less than epsilon, I know this whole thing will be in y. So that means the E naught is actually an interior point because you can move around. This is E naught. You can move around, and as long as the AI has a magnitude less than epsilon, then you will be still inside the convex hull, which is inside the C. Okay, therefore the E naught is an interior point of C. So what we have done so far, what we're trying to get here is that since the E naught is somewhere here, and I know that is corresponding to, if I shift it, I'll get back to the origin, I'll have this shape, and this is my new point. Then I can define the mean coefficient, the functional, as we decided before, and that functional will be Lipschitz continuous. So let's say be the mean coefficient functional of this E minus E naught. Okay, just shift the linear manifold back to the origin. And then we know that this P has all the properties we needed because we have the C is closed. And actually, first of all, because this mean coefficient is functional, it must be non-negative, positive homogeneous, and also subadditive. This is by the property that is mean coefficient theorem, because it's functional, and also the PS must be equal to 0 because the C minus E naught is bounded, right? I should say C minus E naught is bounded. C is a convex set, so C is bounded, and that's why the P of X is equal to 0 if and only if we're at 0. And it's Lipschitz continuous because, as we said, 0 is the interior point of C minus E naught. Okay, and according to this, we know that P, there must be some C1, C2 greater than 0, such that the P of X is greater than or equal to C1 times X norm, that's less than or equal to C2 times X norm. Okay, this X norm is actually how I represent the Y. This to clarify this, I can just say that this X norm is actually the Y norm we defined earlier, because it's going to take into account of the AIs, not the E's, here. Okay, we said that we define the norm of Y to be, if Y is written in this way, I'm only interested in the coefficients. So this part is my X. So the norm of X is just the norm of this A. Okay, this is how I define this X. So we clarify this is just the X. Sorry, this is the X E naught plus X, and this X is just the sum of ai ei minus e naught as from 1 to m. Okay, so this x is just the x value of a, or the length of a. Okay, and now this is true. Well, from here, I can define the mapping between the ball and this C. So let's say I have defined my function f. Now eventually I want to show that this bm mapping to C. I want to show this f is homeomorphic or homeomorphism. So I need to show that f is a bijection or is bijective, and f and f inverse are both continuous, right? And if I can show that, then these two, the bm and c, are homeomorphic to each other. And to show that, let's say for any point z in the ball, I'm going to map it to f of z, and this f of z is defined as, if it's z is equal to 0, and we just shift it to e naught. If z is non-zero, I'm going to define to be that, to be this. Okay, so this PZ is like the Minkowski. It's like I treat this Z as on the plane, E or E minus E0, like treating this as a point in the linear manifold or linear subspace, and this PZ is corresponding Minkowski function of that. So although this P originally was defined on E naught, or defined on E not, or E on C, not on this BM, but I can always treat them in that way. Well, if this is the case, we'll be able to show that this f is continuous. The reason is if z is non-zero, then we can see that this P of z is non-zero, right? And this is norm of z, and they're both non-zero and they're both continuous. So this is a continuous function of z. That's why this will be a continuous function of z. And that's for the case where z is non-zero. But for the case zero, for z is 0, then we can show that the so yeah, I have zk goes to 0. I want to show that the function f is continuous at 0. I just need to show that f of zk converge to 0. Okay. Well, if they're converging 0 and they're not 0, then I know this is just a e naught plus dz over zk or pzk times zk. Well, for this part, I know that it is the zk over p of zk. According to the property of p, it should be bounded between, this just means that the norm of x over p of x is less than or equal to 1 over c1, and it's greater than 1 over c2. So this will be less than or equal to 1 over c1. So if this zk goes to 0, then this is bounded by that, and this goes to 0. So if I take the norm of this whole thing, I will see that this is bounded by some number, but this goes to 0. So the whole thing here will go to 0. And that means this thing will go to E naught. Okay, so if zk goes to 0, then f of zk goes to E naught, which means that it is also continuous when z is at z equals 0. So this is how we show that f is continuous. And similarly, I can also show that f is a one-to-one mapping. So to show that, we can construct the f inverse. And the f inverse turns out to be, so f for any y, where y is the E naught plus x. Right, in this way, E naught plus x. So y is from C, y is a point in C, and it's written as E naught plus x. And I define this to be, actually I can compute this to be the inverse of that. And this is just if y is equal to E naught, I will just take the value of 0. If y is not equal to E naught, that means x is non-zero. And in this case, I'm going to define this to be px over the norm of x times the x. I'm going to show that this is the inverse. Okay, this is the inverse of f. I think I can, for example, I can show that for any y, this must be inside the ball. The reason is if x is inside C, or say C minus E naught, then I know that the P of x must be less than or equal to 1, right? And so the Px over this, if I take the norm of that, it will be less than or equal to the P of x times the norm of x over the norm of x. So this is just equal to 1. And this is Px is less than or equal to 1, so that's less than or equal to 1. So that is indeed a point in the ball. Okay, so I map every point back into the ball. And also similarly, you can show that this one, for any z in the ball, you can show that this is inside the C. Okay, you can also show that it's inside the C. It's because the z over pz how do I say that? I know that pz is, according to the definition, I know that you can add some small number epsilon k so that this is in C, right? You can show that this is in C, and then this whole thing, if this is in C and C is closed, as we said before, then when epsilon k goes to 0, this will be in C, and you are multiplying that, sorry, z, the norm of z. But z is in the ball, so this one is actually less smaller than or equal to 1. So that just means that the whole thing is still in C. So that's all can show that this is also in C. Okay, so that's a mapping. And also easy to show that it's a one-to-one mapping, because as you can see, the z will map to a new point f of z, and they're going to keep the same direction z right here. Okay, so it's along the same line. So if all the complication, most of the complication is from the E naught, but let's say the E naught is 0, then things will be clear. So this is the ball, and then maybe this is the C. So for each point Z in the ball, you just get a corresponding point in the C. For example, it's here. This is the f of Z. Okay, if we just think this E naught as 0, okay, they're along the same line. And these two, if they are equal, if and only if this, say if we got another point which has the same length, then we should be able to show that they keep the, say, z over pz times z is equal to z prime over pz prime times z prime. Then you can see that they have the z and z prime have the same direction. Right, same direction, and it's easy to show that they also have the same length. If you take the norm, and it's easy to show they will have the same length, and that just means z and z prime are the same point. And this is the whole show, is to show that they are actually one-to-one mapping. So we have one-to-one mapping. We have f defined in this way, and f inverse defined in this way. And as we show that the f is continuous, and easily show that f inverse is also continuous, pretty much the same form as that. And this is the continuous function of x. So that shows that f is actually homomorphism from the ball to this C. Okay, so that's the idea. Okay, so you can try this by yourself to complete the details. So f from the ball to the C is bijective, and F inverse are both continuous. And this together implies that the BM and the C are homeomorphic. Homeomorphic to each other. Okay, so that's the proof of this result. So the goal of this result is to generalize the, or get another fixed point theorem. There are many fixed point theorems in analysis. We have not discussed the one before, the Banach fixed point theorem. I'm going to have another fixed point theorem for this B space or Banach space. And before doing that, we are going to combine the corollary just have here and the well-known Brouwer's fixed point theorem from topology to get a new result. And that result is going to be used to show the Schauder's fixed point theorem, which is our goal here. Okay, so let's first recall that the Brouwer's fixed point theorem So idea here is that if we have fixed closed ball in Rn, and I have a continuous mapping from this ball, closed ball, to itself. Then these two together implies that there exists a fixed point of T. Okay? There exists a point in this ball such that Tx equals to x. So this is actually from topology. It has many interesting interpretations here, and I'm going to. I think one of the most famous one is that when you have a map of the world, and then you wrap it into whatever shape, then there will be one point in this map, wrapped map, that is actually the location that you're standing on. Okay, you're holding this wrapped map, and it's actually there's one point. If you drop it on the ground, it's actually corresponding to the exactly location that you are standing. Okay, that's one of the interpretation of that. If you're interested, you can take a look online what this Brouwer's fixed point is. We're not going to prove this here. It's actually we're going to generalize this, because this is the Rn. We're going to generalize this into the infinite dimensional space. And before doing that, let's combine the result we have in the corollary above and this one. So we can see that it doesn't have to be a closed ball here. It could be any compact convex set. The reason is we can always establish a convex homomorphism between a compact convex set and a ball. Right? That's why we can always just consider a general case. So this is the corollary. Consider this to be a compact convex set of Rn. The T is a mapping from C to C itself. It's continuous. Then T has a fixed point in C. Okay, so the idea is pretty straightforward. We know that we can establish a homeomorphism between the C and this ball. Let's say I have a mapping from C to this ball. And this phi is a homeomorphism, as we showed in the previous corollary. And now I can see that the phi inverse t, which is actually, so now the t is from C to C, okay? And I know that from C to B to the ball, I have the phi. And here's the t, so I guess this will be this. So I know that now the composition of the three, which is phi inverse t, phi, this will be a mapping from the ball to the ball, right? So this will be from the ball to the ball. And now I know that by the Brouwer's fixed point theorem, there exists a fixed point. There exists a fixed point x inside the ball, such that a phi t phi inverse of the point x is equal to the x itself. And that also means because the phi is invertible, or it's bijection, so I know that this is true. Okay, so the phi inverse of x, this is the point, this is the fixed point I'm looking for. I know that this point is in C. Okay, now I show that Ty equals to y, that is in C. So that's how we show that the T has a fixed point in C.